Hi, welcome along. Little video about energy in oscillating systems, and hopefully this will be something that's not too challenging. So let's actually take a detailed look, see if we can see what's going on in terms of energy in this oscillating system. I have to say that this is, kind of a nice friendly bit. It really just fits in with everything we did last year. You can see the objects moving up and down, so hopefully fairly obviously when it stops, it's got no kinetic energy, like now. And when it gets all the way to the top, now no kinetic energy. And if you look all the way over on the left, there's a green bar that's zipping up and down that's showing how much kinetic energy it's got. If I just put in the equilibrium line, so as the mass crosses that line, it's got maximum kinetic energy. Not sure why it paused there. Probably my computer's struggling under the load. And when it gets to the end, zero. And then conversely, if we look at the blue line going up and down, when it gets all the way to the top, it's got lots of potential energy. And when it gets all the way to the bottom, it's got lots of potential energy. The potential energy here is a mixture of two kinds. It's a mixture of potential energy due to gravity and potential energy for the energy stored in the spring. And then you can see the third line. You can see the green part kind of going up and down with the kinetic energy, and the blue part getting bigger and smaller. And that line is showing you something really simple. In an undamped system, we'll do damping later, in a system where the energy is constant, we're just transferring energy between kinetic and potential, and therefore the energy is conserved. Okay, and I'll have a go at sketching some graphs of that next. So we continue our look at energy in oscillators, and we're just going to sketch a quick graph of how the energy of an oscillator varies with displacement. I'm going to make sure we've got a few colours available. So a really important feature of this graph is the maximum values of the displacement. So that's obviously going to be plus A, that's going to be minus A. We don't consider the energies ever to be negative, and by convention, we consider the amount of potential energy stored to be zero in the middle. As so often is the case with potential energy, that's arbitrary. Okay, so that's there. That's there. That's there. So this is the potential energy graph. Doesn't matter whether we're dealing with a pendulum or a mass on a spring, a ball rolling on a track, anything that's a simple harmonic oscillator, then that is the amount of potential energy. And it is a parabola. It's varying as x squared. The kinetic energy just has to be the whole thing upside down, doesn't it? So it's maximum in the middle, zero at the edges. And because the total energy isn't changing, we can just have, complete my key. Those two colours aren't sufficiently different really, are they? I do apologise, but I think you get the idea. And then finally, we've got that, which is E total. So that's good. We're now going to look at how they vary with time. Okay. And whilst this isn't very complicated, it seems to throw people slightly more often. Let's make this a graph of displacement against time. And I've just slightly cropped it differently this time to make sure that we're starting at maximum positive displacement. And then this follows the pattern of this equation. It's a cos graph. So the first thing we're going to ask ourselves is, can we draw a graph of how the kinetic energy, I think we'll go potential energy first, varies with time. And we know that the potential energy from here, the bigger the displacement is, the bigger the potential energy. So we know
that these points here, we will have 0 potential energy. And at this point here, we know we'll have maximum potential energy. And I think the thing that sometimes throws students is that we've also got maximum potential energy here, because the energy doesn't care which side of the oscillation you're in. It always peaks as a positive number. You don't have negative energy because you're on the other side. And so what we're actually sketching here, and it's not well, I'm not very good at sketching any functions, but this is a cos squared graph that I'm attempting. And you can see that it's got twice as many peaks, positive peaks per cycle. And then because we know that the kinetic potential energy plus the kinetic energy is always a constant, we can put in our graph for kinetic energy, and essentially it's just peaking like this. So when one peaks, so when the kinetic energy peaks, the potential energy is 0. When the potential energy is 0, the kinetic energy peaks. And presumably, if the red one was a cos squared graph, this is a sine squared graph, and as you know, cos squared plus sine squared is 1. So yeah, that demonstrates the adding up to a constant. Okay, thank you.